Okay, so here is 7.7 moment generating functions. These functions are important for us right now because they are a key to deriving the central limit theorem. Now, actually, if we were in a graduate course, we would use not moment generating functions, but characteristic functions. It's much more convenient, it's a much better tool to use for getting at the central limit theorem and for many, many other things that you would want to do. But characteristic functions involve complex numbers, and I think the choice of using moment generating functions in this textbook is just to avoid complex numbers and the complications involved in that. It's not really complications, but it would mean that we'd have to assume that you know things about complex numbers. And I think for the target audience of this textbook, they don't want to assume that. So we're using moment generating functions instead. So here's the definition. The moment generating function, maybe MGF, if I need that acronym, we'll use that, of a random variable x is defined as m of t, or if we need to specify that the random variable that it goes with, m sub x of t, and it is the expected value of e to the tx. Okay, now you know expected values, depending on the random variable, an expected value could be an improper integral, or it could be an infinite series. And in both of those cases, the object, integral or series, might diverge. And when it diverges, the expected value doesn't exist. So expected values don't necessarily exist. So that means that the moment generating function might not exist. For some t's it will. It always exists for t equals 0, right? M of 0 is just the expected value of e to the 0. It equals 1. It always exists for t equals 0, and it always equals 1. But for other t's, it may or may not exist, depending on if that expected value exists. But let's say that it does exist for at least on an interval that contains 0. And not only does it exist, but let's suppose that it's differentiable. Okay. Well, then I could compute m prime of t. That would be d dt of the expected value of e to the tx. Now what I can do with that, the next step that I could do, the justification of this step goes beyond our class, but under the appropriate hypotheses on the random variable x, I can reverse the order of the expectation and the differentiation. Now if I differentiate there, then capital X is a constant, and so I get the expected value of x times e to the tx. And what's useful about that is that m prime of 0, if you plug 0 into there, e to the 0 is 1, you get the expected value of x. So if you know the moment generating function and you can compute the derivative at 0, that gives you the mean of the random variable in question. Okay, we could do it again, right? I could compute m double prime of t. So two derivatives with respect to t of the expected value using advanced theorems justify reversing the expectation and the differentiation. Differentiate it twice, and you get x squared e to the tx. And so m double prime of 0 gives you the expected value of x squared. And then this pattern continues, and in general, the nth derivative of m at 0 is the expected value of x to the n. And those numbers, for each n, you look at the number the number that you get when you compute the expected value of x to the n, that sequence of numbers, those are called the moments of the random variable x. And so this formula here is why m is called a moment generating function, because using that function and calculating its derivatives, evaluating it at 0, you are able to generate all the moments of the random variable x. So let's look at some examples and compute some of these. So here's example 7a. All right, so x here in this example is going to be binomial with parameters n and p, and we want to compute the moment generating function. All right, so we go to the definition. It's the expected value of e to the t x. Okay, x is discrete, so e to the tx is discrete, and we're going to sum over all the possible values of x. X can be anything from 0 to n. And we have e to the tj times the probability that x equals j. Okay. X is binomial, so that's going to be n choose j times p to the j times 1 minus p to the j. No, not to the j, to the n minus j. And let's rearrange that a little bit. We'll write it as sum as j goes from 0 to n choose j, and then we can write this here as p e to the t to the j, 1 minus p to the n minus j. And then as a last step, we'll use the binomial theorem. So if you go back and look at the binomial theorem, you can recognize that this sum is the same thing as p e to the t plus 1 minus p whole thing raised to the nth power. So if x is binomial np, then this is the moment generating function. Okay. Let's look at another example. 7b. Let's take a Poisson distributed random variable with parameter lambda, figure out its moment generating function. All right, again, we're just going to go back to the definition. All right, so I have the expected value of e to the t x. Okay, so we're going to sum. The Poisson can be anything, any non-negative integer. Then I have e to the tj times the probability that x equals j. All right, x is Poisson. So that probability is e to the minus lambda times lambda to the j over j factorial. Okay. I could pull out the e to the negative lambda, and I can write this as lambda e to the t to the j over j factorial. The sum of that series is e to the lambda e to the t. Okay. And I could put all that together as e to the lambda e to the t minus lambda. And it's a little bit easier to read without the nested e's. So the outer one, let's use exponential. Factor out a lambda in the exponent, put e to the t minus 1. So that right there is the moment generating function of a Poisson. Okay. Do another one. Do a continuous one this time. So 7c. X is exponential with parameter 1. And we want the moment generating function. All right. As with all the others, start with the definition. Expected value of e to the t x. This time x is continuous. Density is supported on 0 infinity. So we have the integral from 0 to infinity of e to the t little x times the density of x, which is e to the negative x dx. All right. Do this calculus and get lambda over lambda minus t if t is less than lambda, but the improper integral there diverges when t is greater than or equal. Well, wait a minute. Where did I do? I did 1, not lambda. Sorry about that. So this is what we get if t is less than 1, but if t is greater than or equal to 1, that improper integral diverges, so it's undefined. It does not exist. The moment generating function does not exist if t is bigger than or equal to 1. However, it does exist in an interval around 0, and it's a very nice function. They're infinitely differentiable, so we can differentiate as many times as we want and calculate all the moments of the exponential. And I'm not sure why I did lambda equals 1. I guess because the lighting is bad here and I'm reading in the book and I thought it was a 1, but it's a lambda. So if you want to generalize, then see the book. It's not much different. If x is exponential lambda, then the moment generating function is lambda, that's a terrible lambda, lambda over lambda minus t if t is less than lambda, and doesn't exist if t is bigger than or equal to lambda. And of course, lambda, the parameter of an exponential, always has to be a positive number, so this moment generating function is going to exist in an interval around 0. The last example, I don't want to go through the details now. We've seen a lot. I'll just highlight the result for you. They go through the details in the book. So if z is a standard normal, then the moment generating function of z is e to the t squared over 2. That fact is going to be very important when we go to look at the central limit theorem. And then if x is normal with mean mu and variance sigma squared, so remember that means that you can write x as mu plus sigma z, then the moment generating function of x, I will go through this calculation. This one you can look in the book. You have to do an integral against the density of the standard normal. But this one would be the expected value of e to the tx. So that's the expected value of e to the t times mu plus sigma z. I can write that as the expected value of e to the t mu times the expected value of e to the t sigma z. This thing's not random, so I can pull that out of the expectation. And think of t times sigma as just a single number, then what you're looking at there is the moment generating function of z evaluated at t times sigma. So that's e to the t mu times e to the t sigma squared over 2. Or a little easier way to write it, the exponential of sigma squared t squared over 2 plus mu t. So that right there is the generating function of a general normal random variable, normal mu sigma squared. I want to talk about some important properties of the moment generating function and what we use it for. We're going to make one more part here. I think the next part probably be the last part of this whole chunk of material. Okay, so see you in the next video.